Okay, good afternoon. So this presentation, which is on going to be considerations really for improving knowledge-wise for the operation of swimming pools, picking up where we leave off with the National Pool Plant Operators Certification and really just enhancing a bit of the knowledge on that. So it's just going to be about building on the foundational knowledge of the NPPO certificate or another equivalent swimming pool technical operator as set about by PUTAG actually, whether it's STA or PALM or iOS or any of the other groups. So if I said to you guys, get a picture of a filter in your heads, we'll probably all come up with this or something very similar. If I said draw a picture of a filter. Now, is that more or less what everyone thought when I said picture this? And the reason why is because we've had no changes really in the last 100 years or more. So this is a filter from, at the far left, from 1906 at a site in North London. This is a filter from the 1960s. And then this is a filter from the last 5 years. No real changes. So you'd have thought after all of that time we'd have actually mastered filtration using sand as a media or a suitable equivalent like crushed glass. So why is it then when we go about from site to site we see such different standards in pool water quality in terms of filtration if we've been doing it such a long time and nothing's really changed? So, if we presume that we have a fair idea, we must be able to work out what the filtration velocities are going to be, what methods we can use to actually enhance that, like coagulants, etc., the type of media that we actually use inside the filters, when we actually carry out a backwash, how long should we backwash for, how we actually identify other areas that could improve the filtration, and do filters compromise the pool water chemical levels if we don't get it right? So it's not just a simple thing of straining out the pollution, but there's a lot more to it than that. So let's start off with the basic maths, calculating filtration velocity. So how many people here get involved with doing any spec work at all? Little bit? So generally the way that things run most of the time, and I certainly started with this, was by taking the circulation rate from a flow meter, dividing it by the filtration area, which will be the number of filters, and then the diameter of each of those filters. So for this example, we got 76 meter cubed per hour as a flow rate, and then that's being divided over 3 filters, and these filters are a diameter of 1.2. So that's 1.13 each, 3.39, and that gives us 22.4 meters cubed per hour. So that's sitting square in what we would call medium rate filtration, which is the prescribed velocity that we should have through sand filters to actually achieve very good removal rates, even of some nasty critters like cryptosporidium, if we got a use of a coagulant. But it's not quite that easy. We've got a bit more to consider than just the diameter of the filters and the number of them. What we're going to do now is actually take a look at the internals of a filter and how that can make quite a big difference. So when we're looking at the hydraulics, we have to understand that water is always going to take the easiest route from A to B. With that, we've got to ask ourselves if there are going to be any factors in terms of operation, design flaws, or maybe even issues with the maintenance and ongoing repairs of filters that are going to affect the flow rate. Will the chemistry of the water come into play and make a difference? And then the actual media itself, is it just as simple as sand, glass, pretty much they do the same thing, or is there more to it? Well, let's take a look at the ideal model, and then we'll move away from that and look at what we actually see in the industry, or I've seen going around from place to place over the last few years. So if Carlsberg built filters, they'd probably be like this. Okay? And there is one actually over on the Golden Coast stand, okay? Golden Coast have got one of these, they chop the side off it. But Calplast filters are manufactured in northern Spain. They're very, very well constructed, but the way that they actually think about the distribution of the water and getting even velocities through the filter, not many people are doing it to the same level. You've got other filter manufacturers that do a really good job, but I think the amount of thought that goes into it and then actually being innovative, Calplast are doing a fantastic job, and they've been going for about 50 years. So, if we don't have an ideal example, what might we come across that's going to actually affect things and could actually lead to some big operational problems? So the main thing is going to be an uneven distribution of water through the filter, which is going to reduce the effective surface area of the filter, pushing velocities higher in certain areas and lower in others. This could, of course, create risks, and that will have to have an impact on your operational procedures and indeed your risk assessments, especially for things like your emergency action plans for gross contamination. So this diagram actually comes from the sort of standard pool plant operators course, and this is showing that if you've got a very small diffuser, it's just assumed really that if you take that whole surface area of the filter, divide the flow rate across that, that's going to give you a velocity. But is that going to be uniform throughout the whole media bed? It should be, but if the diffuser's too small, these two areas that are marked out in red will often become dead spots, and will either have the water that doesn't flow through there at all, or even worse, every time we backwash and we get a bit of flow going into them, the water and the pollution within it stagnates in those areas, leading to an increase of biofilms and also premature lifespan for the actual media needing to be changed. So I'll give you a few photo examples of what has been causing this in real life. And if we take a look at these beauties here, these are things that I've seen over the last 10 years. There's a lot more than this, but I was going through on the weekend trying to find the best photos to sum things up. Take a look at the top left, the size of that filter, and then take a look at the delivery pipe and the diffuser, and tell me that that's going to give an even spread of water across the whole surface area. Well, it's not going to. Give it long enough, and then this is what you're going to see. The photo that you've got there in the middle, see where the media around the edges has turned more like sand and cement. And actually, what we've got really big issues with that is going to be premature lifespan of the filter, incomplete backwashing, and therefore a lot of biofilms. Here we can see at the bottom left a lot of clumping, so we've not quite got to that stage. And this has actually got a wider diffuser, but it's still not doing enough. The filter in the middle, we can see that with the water for the photo which is on top, and you can see there, this was about a year apart in between doing the filter internal assessments. So within a year, it's really actually degraded in a very short matter of time. Here we have a repair job which is done into a filter, and the media is still quite good, but without the diffuser, the water's only going to be going through the center of the filtration bed. And above, is probably the best one that I've seen in all my time. There is no central pipework or diffuser. Basically, the manifold on the front of the filter was the inlet to the filter, and they were losing copious amounts of sand every time they backwashed and wondered why. Okay? So with these, the kind of issues that we're going to get are going to be eventually costing us a lot more money. Initially with chemical costs. Of course, then if we're losing media, we're going to need to be paying for that. And then the media actually getting destroyed in a very short amount of time and needing to be replaced in quite quick order. Other things that we can see is where the water is traveling at a high velocity through the center of the filter, which is this part just here, what we've actually got is high rate. So the flock's not going to settle at all, and the water's going straight down through the middle, down to the laterals. And as you actually make your way out to the sides, this is the same filter, you can see it solidifies more and more and more as the velocity becomes less and less and less, and there's no flow at all, and you've just got dead spots around the edge of the filter. Okay. Equally, if we have a filter and the diffuser's not large enough, we'll actually get dead spots down the whole side. Now, I know with a lot of steel filters, people might use air scourers and actually try to shake the media up to give it a good backwash, but if the diffuser's not wide enough, the air's only going to be going in one direction. That's the same as the water. So we're going to end up with dead spots along the whole outside circumference of the filter vessel itself. So we're going to end up with very, very similar issues, okay? And then an increase in biofilms and large portions of the media actually not doing any good job at all. In reality, we'd expect that from a filter with a lateral system, as we can see here on the left. When what we should have is a full spread, as this example is here on the right, where we know that we're going to get a good surface area with good flow going right the way through. But the diffuser has to be very wide, and equally the laterals need to be spread very wide as well. Now, if you're fortunate enough and you actually have windows where you can see into the filter, viewing windows, what we should have is what we've got here on the right, after backwashing. If we got something more like here on the left, even following a backwash, then that is showing that there's not much movement at all in particular areas of the filter. We're not able to get a very good backwash. Initially, you might start backwashing a brand new media bed and it might be able to get a bit of movement, it might all be able to lift, but after it starts clogging up with more and more pollution and grease from the bathers, eventually it's going to solidify and it will again be from the outside edges working its way in. And probably your first telltale signs, before it gets this bad, you'll be seeing failures on your microbiological testing, increase in chemical costs and chemical consumption. But if you use more chlorine, you're going to use more acid. What's going to happen to your water balance index? TDS is going to go higher. The more acid you use, the more alkalinity you take out. And therefore, we're also going to see some progressive damage even to vessels, especially if they're steel, and other plant equipment, valves, pumps, heat exchangers, UV systems, anything metal in the plant room, and of course the pool finish itself. So the left, inadequate under drainage. The example on the right is pretty good. If you do backwashing and following the backwash, we see these pressure gauge differentials still being very large. That is another indication that there's still a lot of resistance within the media bed even after we've done that backwash. And that's the same with both of these examples. Okay? Obviously, the one on the right is quite a bit more pronounced than the one on the left, but this is still not acceptable. Okay? It's still too great a difference, especially after just conducting a backwash. And if we can't backwash the filter, we can't get rid of the pollution. If we can't get rid of the pollution, it's a food source for the bacteria to feed on. Biofilms will form, and then it's just downhill from there. Other issues that we can have with backwashing, I think this follows on quite nicely from Lynn, who was speaking just before me, is just ask yourself a question. When you actually do a backwash, and we've got quite a few pool operators here, a few, so you manage to backwash, sight glass always goes clear? Yeah, happy days. Have you been to sites where they backwash, or you might have spoken to some of those staff, and they can't backwash for the full amount of time? They flood the drains. And they never actually manage to clear the sight glass. So even if we've got a good diffuser, good lateral system, if our drainage capacity is not enough, then we're not going to be able to backwash adequately. And we've got to make sure that we avoid incomplete or incorrect backwashing. Otherwise, with more contamination around, we're going to have issues where combined chlorines raise. And if there has been an incident in the pool and we're trying to do a thorough backwash after a crypto poop, well, we might just end up recontaminating the pool again by just washing it back in if we haven't actually cleared everything out of the media. So some examples of what we can do to get past that. And this was a site which was Originally built in the 1950s as a swimming pool, but it preceded that as an air raid shelter for the Bank of England in the Second World War. And they changed the air raid shelter into a pool, but of course the sort of drainage they put on it was what you'd probably expect from the 1950s. So with that, now having a sort of modern setup, it could have done with 2 filters of about 1600 diameter, giving a surface area of about 4 meters squared. But the drainage just wouldn't be able to cope. Now there's a few ways to work around it. You could still go with the 2 very large filters, and then what you could end up with is having a backwash tank. So you backwash into the tank fills up, and it's slowly letting water out to the drain, so you're actually going to get the velocity up for backwashing a large filter. Without that option, why not just put in many smaller diameter filters and get your surface area that you need for your filtration and your turnover times adequate, but actually have numerous filters. I think this site ended up with 10 filters, and they were all 0.8 of a meter diameter. One of the great things about this is that on a backwash line, which is coming out from each filter, you put one of those filters onto backwash, and the velocity going through it's going to be much higher naturally, while all the other filters are running on normal filtration mode. And then you're guaranteed you're going to have a really thorough backwash without turning the pumps on and off. No worries about strainer baskets or anything else. So the devil's in the detail, but things can be calculated in such a way to make that really easy, especially where sites have some access issues as well. This is quite a good way to do it, and then you've got a really healthy redundancy. If you've got any maintenance issues and you take 1 out of 10 filters online, no one's going to know any different. Okay? So, when it comes to the media itself, we've got to think about multigrade, especially where we have laterals. Now, multigrade, sometimes putting gravel in around the laterals, and then on top putting sand, or with glass it would be grade 3, then grade 2 and grade 1, is quite important because the laterals need the support. 2 reasons. One, the larger gravel grade will allow for the flow of water to actually distribute around the gravel a bit more evenly. So even if the laterals are not fantastic, the gravel can actually help spread the water. And when you're backwashing, the gravel won't lift. Because of the larger gaps in between, it lets the water pass through and it doesn't lift as the sand would. And that keeps the laterals very stable. If the laterals are not stable, eventually they'll just flex, flex, flex until they snap, like we can see here. But this was quite a long process at this pool. The first thing was, okay, flow rate's gone down, heating's not really as it should be, and we got to tell all the customers that we have a new beach zone in the pool. The photo along from that was actually the UV chamber, got filled with media, and that can be an issue, especially if you do have some issues and you actually wipe out the quartz sleeve and the lamp. The strainer then has to be there to catch the broken shards of glass. But this completely blocked up, more or less, and the flow rate went from 150 down to about 20 an hour. And of course, the heating dropped off, everything eventually got cloudy. So the next steps, sussing out which filter it is, dropping all the media out the filter to find the culprit. Okay, and that's what we have here. So if we got laterals, we must have a gravel grade media. If you actually go onto the rose nozzles, that's irrelevant because they're actually all solid in a resin right down on the base of the filter itself. And there are a few examples around that you can see in the showroom. We've also got to think about coagulation. So with coagulation, we're trying to enhance the removal of dissolved or colloidal matter, including even biological matter like cryptosporidium, within the filtration media. Normally, most filters are going to be, when they're in good condition, they'll be taking out about 8 to 10 micron diameter of pollutants. If we have higher rate velocities, we're not going to be able to form a flock inside the filter itself. If our water balance is bad, our total alkalinity is all over the place, we're not going to be able to form a flock either. It's got to be just right. Hence, I think the trade name Goldie flocks, right? Not too much, not too little, just bang on. Okay, so if we've got low alkalinity, your risk assessment, if you're using coagulant, is out the door completely. Okay, it's not going to work. There are some filtration medias, like AFM really, is the one that comes to mind, advanced filtration media, which is going to be resistant to biofilm growth. They make it hydrophobic, and we put a filter online last week at a hydrotherapy pool, so new filter in, new media in, and some of the excess media on doing the first initial backwashes, of course, gets into some of the pipe work and makes its way back to the pool. But this media is floating, showing that it's hydrophobic. It doesn't just sink down to the bottom of the pool. And often we can see the media actually floating inside the filter itself when we first fill it with water. Okay. There are, I think, going to be other presentations on AFM, so I'm not going to tread on anyone's toes with that, but it's definitely worth looking into with Trident Aqua. We've seen some really, really good results, lower use of chemicals, better pool water quality, and actually sometimes some water savings as well, because we're not having to backwash for as long. Okay. So, when it comes to the alkalinity side of things, normally we're introducing sodium bicarbonate to raise those alkalinity levels, even in hard water areas where we might get a lot of natural alkalinity from the mains. Now, normally it's going to be made of carbonates, bicarbonates, and some hydroxides as well that will be present in the pool water. We try to maintain it between 80 and 200 milligrams per litre. If it goes down too low, we get pH bounce. If it goes too high, we get pH lock, but I've never really seen anyone have issues with that. Most pools struggle to maintain the minimum acceptable level for total alkalinity, and a lot of those pools are pumping in polyaluminium chloride or another coagulant, thinking that it's doing a job which it just can't do when alkalinity levels are very, very low. They should be tested weekly, and adding bicarb is the textbook answer for how to deal with it. Has anyone tried dosing bicarb and actually getting the alkalinity levels increased in swimming pools? How's that working for you? Yeah, it works on the day, doesn't it? And then what happens? Then your pH sensor goes, oh, hang on, the pH has gone up. Then what does it do? Bungs in the hydrochloric acid or sulfuric or bisulfate, and then the TA, total alkalinity, tanks. TDS goes up, and the water quality gets worse. The typical dosing system that we'd have is going to be this, where we're just slug dosing it in nice and slow, and what we should be seeing is it actually having this almost magnetic effect inside the filter where it's forming flocks and it's drawing the pollution to itself. Okay. If you're really struggling and you're still dosing it by hand, I would recommend still putting it in, but really, really minute amounts continuously, really slowly. I would always say, if you can, dissolve it in a tank, pump it in the same way that we pump in other chemicals, almost like the way we do sodium bisulfate, but our injection point's got to be quite key, okay? Where is it most important to have highest alkalinity levels? Well, if we've got coagulation as part of our risk assessment for dealing with gross contamination in the pool, my suggestion is put it in pre-filter. That way, it's going in straight after the sensors are picking up the pH and chlorine readings, so we know that it's not going to be affecting those sensors and it won't lift the pH until right at the end, after it's gone all the way around the system. So we're going to end up with more localized areas within the pool plant system where the alkalinity can be manufactured deliberately to be higher. This reminds me of if we've got any old school people here where we were using something like dolomitic media. So back in the day when chlorine gas was quite prevalent, when chlorine gas is added to water, we get hydrochloric acid as a byproduct. Hydrochloric acid, concentrated inside steel filters, is a recipe for needing new filters. So what they used to use is dolomitic media, which would be crushed up, almost like limestone chips that would go into an actual filter vessel itself. And what would happen is every time it got a bit too acidic with the chlorine gas overdosing, then it would actually neutralize the acidity with the dolomitic media. So if you've got steel filter vessels, it can also be a benefit adding the sodium bicarbonate at that point. And your plant system would look something like this. Okay. So if we put the sodium bicarbonate in just pre-filter, what we're guaranteeing is where the coagulant's been injected, we're actually going to get that localized higher levels of total alkalinity, ensuring that actually within the filter itself, we're going to have an acceptable flock bed actually being manufactured because it's got the ideal conditions. The other benefit is with still filter vessels, we're actually pushing up the Langelier index or water balance index within the filters. And we have that other bonus of it's got to go all the way around the system before it gets picked up again in the measuring cell. Okay, so there's been a couple of ideas put across. I'm just about out of time. So does anyone have any questions or comments? Things you might have noticed?
With your rose nodules and the larger filters, are they having one just standing on top, or do they still need to roll back on top? Like that they're in bed, like they said, the resin,
If you've got rose nozzles, you should be getting away with just a single grade of media. Okay. Anything else? Okay. No disagreements. No one's looking for an argument, no? All right, okay. Well, thank you very much for attending, everyone. Okay? Take care.